Oh, this is amines 5, the 5th lesson on amines. Like the previous lesson, it's not really about amines at all, and it's more about amides again, specifically polyamides, okay? So really this is about a bit of polymer chemistry, okay? So let's kick off with some starter cues. Here they are. Pause the video and answer these questions. Just a quick reminder that if you are not pausing the video and you are just waiting for the answers to come up and copying them, that is an exercise in futility and you are wasting your time. If you're not going to at least try to answer them, there is no point in you watching this video. So by now, I assume that you've had a go at answering these questions. Let's have a look at the solutions. So for the first one, I've given a couple of equations as well. I didn't actually ask for those, but just to be kind of clear, I've shown the generation of the electrophile by the reaction of ethanoyl chloride and aluminium chloride. Then the mechanism has the acylium ion in it, the positively charged ion that you get by removing the chlorine atom from ethanoyl chloride. And it's the typical electrophilic substitution mechanism with the broken aromatic ring and 2 curly arrows. All right. I've also shown the equation, given the equation to show the regeneration of the catalyst. Again, if you didn't do those two things, it's not that big a deal, as long as you got the idea behind the mechanism. So for the second one, this is one of those examples where it involves an aromatic ring, or at least, sorry, there is an aromatic ring in the structure of one of the reactants, but actually it's completely kind of irrelevant. So phenol hydroxybenzene is an alcohol, okay? And although there's an aromatic ring, this is a nucleophilic addition elimination, where an alcohol reacts with an acid chloride to make an ester, and it should look like that, okay? So again, I've mentioned in the aromatic topic that that is quite a common theme, where you might think that the aromatic ring is going to take some kind of part in the reaction because one of the reactants is ethanoyl chloride again, but actually it's kind of irrelevant this time around. One of the key signifiers here is the fact that there's no aluminium chloride present to catalyze the generation of the electrophile, like we mentioned in the previous step. So just kind of process that, be ready to move on. Okay, so polyamides. The facts are that they are a kind of condensation polymer. Okay, so there are two kinds of condensation polymer you're supposed to know about, polyesters and polyamides, and we're going to be looking at polyamides. Their general structure, I mean, I've kind of, simplified a little bit here, but generally speaking, right, they have this general structure, and we'll have a look at what R represents in each of these cases further down the line, but key things to point out. The first thing is we have an amide link in the middle. Okay, so that is in the middle of each unit of the polymer. Okay, then what we have to imagine is there's kind of a bridge between the NH on one side and the CO on another. Of course, these two sets of functional groups are not connected, right, to each other, but they are connected. For example, this one is connected to another carbonyl group in an adjacent part of the polymer, but we don't draw that because of how polymer diagrams work. You don't draw everything in the polymer because the whole point is polymers are massive, and so you only draw a small subsection. Okay, but it's the same logic over here. There would be an NH in an adjacent part of the polymer over there as well. Okay, so let's just get rid of those and talk a little bit more about polymer diagrams in general. So this is classed as a polymer diagram because it has the little n. If we take that away, and sometimes we take the brackets away as well, right, then the thing that we're looking at is no longer called a polymer diagram, it's now called a repeating unit. The easiest place to learn about this really is when you're first looking at polyalkenes, right, polyethene and things like that, for example, all right? But there's this kind of distinction to be made. So the repeating unit basically just shows you this abstracted, kind of isolated section of a polymer. If you stick the brackets and an N on, that is supposed to represent the entirety of the polymer chain. And it might seem like a weird distinction to make, but it is something that we do. One thing I'll point out is I usually draw the repeating unit with the brackets, just without the N. That's because I think it's easier to explain where the unit ends if there's brackets there, and the AQA are totally fine with there being brackets in a repeating unit diagram. It's just that they might not be there in the mark scheme. Okay, but they won't penalise. They will penalise the little n, but they won't penalise the brackets. So, right, what about the structures that make this kind of type of polymer? So, R1 is obviously going to be some carbon atoms, but the point is that that section, right, represents two possibilities. It could either be something called a dicarboxylic acid or a diacid chloride. And we're familiar with both those functional groups from the carbonyl group topic. R2 represents a diamine, which is basically just something that's got an amino group at both ends. I suppose I should clarify that really what I'm saying is it's not just R1, but this whole section, it comes from a carboxylic acid, a dicarboxylic acid. And also this isn't just R2, it's this whole section that comes from a diamine. So as appropriate, pause the video and make your notes, and then we're going to have a look at some specific examples, because this is obviously a generic structure. Okay. So here's our first example to look at, keeping it nice and simple. Ethane dioic acid is the simplest dicarboxylic acid we can make, because it's got two carbon atoms and it's got two carboxyl groups. The fact that it has a carboxyl group on both ends of the molecules is what allows it to form a polymer. If it was only a normal carboxylic acid like ethanoic acid, it could form an amide, as per the previous lesson, but it could not form a polyamide. The diamine that I've chosen for this first example is ethane 1,2-diamine, which is not the simplest diamine that you can have, but I use it quite a bit as a crossover thing because you should be familiar with the structure if you've studied transition metal chemistry and bidentate ligands. It's not acting as a ligand here, that's not relevant, but it's just something you are familiar with. So once again, because it's got an amino group at both ends of the molecule, that's what allows it to polymerize. And the idea is, just to sort of simplify things a little bit, if we say that that's a little red circle, and that that's a little blue circle, of course, what we're looking at here is the formation of a polymer, right? Which in reality is going to be red, 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 and so on. But intermediate to those, there will be a load of blue circles. And what we're getting at here is it is an alternating structure where you get the dicarboxylic acid part, followed by the diamine part, followed by the dicarboxylic acid part, and so on. Okay, so your next job is to pause the video and try to draw the repeating unit of the polymer you would get from these specifically. If you're feeling insecure about how to approach that, I want you to go back to this structure, look at your notes for this section. It is the same structure, but instead of there being R1 and R2, we have to reflect the actual nature and atoms present in these monomers. So pause the video and have a go. Okay, so our repeating unit would look like this. I guess it's worth pointing out there's kind of nothing in between the two carbonyl groups, and that's because ethane dioic acid is just two carbons, both of which are carboxyl groups, right? So there's nothing in the middle there. Then there's two carbons in the middle of the diamine section, which reflect the two carbons that were present in ethane 1,2-diamine. I've got brackets. If you don't, that's all right. But your structure should join up in the same way mine does. And it should not have an N because I asked you to draw the repeating unit, not the polymer diagram. Okay, let's continue with this kind of practice. Here's another job. It's a polyamide again, obviously. But this time your monomers are butane dioic acid and propane 1,3-diamine. Okay, and just to increase the level of challenge a little bit, I'm not going to give you the structures of the monomers this time, although I will show them as a hint very soon. But the idea is you should pause the video, draw the structures of the monomers, then draw the repeating unit for the polyamide using the structures of the monomers. So pause, draw the monomers, try and draw the repeating unit. Okay, so you should really have an answer by now, but if you were really, really struggling to get going, those are your monomers. It's not super complicated to draw them, but just in case, if that was your kind of roadblock, then you can pause the video and have a go at drawing the repeating unit now. Okay, so I'm assuming that we have attempted at least now, all right? So again, you're basically just transposing, meaning just copying, the middle section of the monomers down into the polymer diagram and making sure that the polymer diagram is reflective of all polyamides, right? Again, that just goes back to the bit from the beginning. There's an amide linkage in the middle. There's an NH on one end pointing this way and a CO on that end pointing that way. And remember, it's this kind of abstracted thing where the bracket just basically, the bracket, if it's there, basically just kind of acts as a bit of punctuation saying, look, your polymer just carries on and repeats like this, but you don't need to draw it. That's the whole point of a repeating unit diagram. I should point out that, to be fair, you could do these in a reverse order. It doesn't have to be the order I've done them. So what I'm saying is, if you had the section of a repeating unit that came from the dioic acid on that side and the section that came from the diamine on that side, you could absolutely make a correct structure doing that. It's just that it's not logical to do with how I've presented it to you. But obviously, I'm just saying there is that flexibility. Okay, you would have to reverse the orientation of your amide bridge, though, between the two units, if you did that. Okay. So here's a famous example of a polyamide, Kevlar, right? Which I guess is probably a trade name for a material. Most famously, you know, body armor for stab-proof and bulletproof vests. Okay. So Kevlar is, amongst other things, probably made from a polyamide, and in this case, it has some aromatic rings in it. So it's made from a polyamide of benzene 1,4-dicarboxylic acid and benzene 1,4-diamine. Okay. So this is the same task as before. Pause the video, draw the monomers if you can, and then draw the repeating unit. If you're struggling to get going with the monomers, once again, I'll show you them and you have an opportunity to pause and put them into polymer form. Okay, so there's benzene 1,4-dicarboxylic acid. There's benzene 1,4-diamine. Sounds complicated, but in reality, you're just kind of doing the same thing as what we were doing already. So here's what we should have, right? It's actually a nice looking, tidy structure with those two benzene rings in it. Another one. So this thing, nylon 6,6, there's actually varying forms of nylon. We'll talk about what the 6,6 means in a minute. But one of the most famous kind of applications of this is as rope material, but also obviously clothing. It's a synthetic material for clothing. This is made from hexane dioic acid and hexane 1,6-diamine. Okay, so this is the same task as before. Draw the monomers from the names, then try and draw them into a polymer. Couldn't do the monomers? I hope you could, but if you couldn't, this is how I'd draw them. Notice how there's been some condensing here. If you did them in full, it's totally fine, obviously. But because the diagram's going to end up pretty large anyway, it kind of makes sense to squeeze your CH2s, your methylene groups, that's what they're called, into brackets and use a subscript to denote how many there are. something that's worth pointing out is the subscripts are different, and that's because in hexane dioic acid, 2 of the carbon atoms in that chain are in the carboxyl groups, this one and this one, and you have to show those. So if you add those 2 on, you've still got 6 carbons, whereas in hexane 1,6-diamine, all 6 of your carbons are in that kind of middle chain section, just in case that looks a little strange. So then, if you weren't able to draw the monomers, pause the video and have a go at doing the polymer diagram now. Otherwise, we're about to move on and look at it. There we go. So again, by now, you're probably seeing that actually, although polyamides look really complicated when you see them in, exam questions and stuff like that, actually the logic behind them is always the same. As long as you understand the nature of the amide link, and you understand that if you have a dicarboxylic acid and a diamine, that actually, drawing the structures isn't that complex. Okay. One final thing. We said the name of this polymer, trivially, is nylon 6,6. Okay, if you're wondering what the numbers refer to, it's to do with the length of each carbon chain, right? So remember, we started with hexane dioic acid and hexane 1,6-diamine, right? That basically nylon 6,6, it's coding that in this section there are 6 carbon atoms and in this section there are 6 carbon atoms. That's basically what it's saying. And there are different forms of nylon where maybe the length of that section is different and the numbers in the name are different. Have a look at the Wikipedia article on nylon if you want to see more. Okay, let's have a look at a special case, right? Another type of polyamide that we've already mentioned several times is polypeptides. Now, one of the things that's special about these is I'm looking at this and I've got 1 monomer. In every other example I've been looking at, there's been 2 monomers, okay? So 1 monomer only. This is special, and the reason this can work is because of the nature of amino acids. They have an amino group on one end, they have a carboxyl group on the other end. Okay, everything else we've looked at has got 2 of each, but this has got 1 of each. Okay, what that means is that this amino acid effectively could self-polymerize, meaning it doesn't need anything else to react with. Okay, so you take this and you take 3,000 units of it and it can make a polymer. It can make a polyamide, right? In biology, it's not going to, because the specific sequence of amino acids has a much more important role. It's not just a kind of long repetitive chain with the same amino acid, but I'm saying it has the sort of potential to. And obviously, actually, even if this was any old amino acid, and we used the amino acid notation of an R group to show that there's something variable in that spot, obviously the logic's still there, okay? So we've already touched on this a little bit because we did some stuff on dipeptides and tripeptides in the previous lesson. But anyway, pause the video and have a go, see if you can draw the repeating unit of the polymer you would get from glycine. Okay, so the outcome here is it's shorter, right? It would just look like that. And this isn't the same as the other polyamide structures we've been doing, and it's because of this self-polymerization that it can perform. Like I said, you're not going to see a polypeptide like that because they tend to have variable sequences of amino acids that then influence the structure of proteins. That's a big part of biochemistry. But I'm just saying, if you did have something like this that could self-polymerize, then it would look like this as a polymer. Well, the repeating unit would look like this. Okay. Final little section. All right. The biodegradation of polyamides, right? So polyamides and polyesters, in fairness, are biodegradable. And this has to do with the fact that they're formed by condensation, and functional groups which are formed by condensation reactions can typically be reversed through hydrolysis reactions. We talked about the hydrolysis of amides a little bit last time, okay? And the hydrolysis of polyamides is a similar story, where you can add water across the amide bridge and you can split that bond apart, essentially. Okay, The reason this is important is because it has to do with kind of the disposal and lifetime, basically, of materials that contain polyamides. Obviously, if they're biodegradable, depending on the time scale, then the impacts on the environment are slightly lessened. Okay, contrast that with polyalkenes. We'll have a look at that very shortly. Okay, so just to be clear, adding water across the amide linkage would return a carboxylic acid and an amine. And then just a reminder about addition polymers like polyalkenes. These things are very resistant to hydrolysis because they don't have any polar functional groups. They are full of very non-polar carbon-carbon single bonds and carbon-hydrogen single bonds. And so they are resistant to hydrolysis. They can't be attacked by nucleophiles or anything like that. Okay, so that's the end of this lesson. The only thing that we didn't cover, which I've realized as we've worked through, is acid chlorides, diacid chlorides. Okay, so I'll just sort of speak to that very briefly, right? Just by sort of, changing the rules up here a little bit. Okay, so let's say that we keep the diamine the same. But we change to this molecule, okay? And that combination, I'd like you to just have a look at. Don't worry too much about the name of the mono and all that kind of stuff. Actually, it is an acid chloride that gets used in the demo that we often do at A-level for making nylon. But that doesn't really matter for now. In reality, this doesn't really change the outcome, but there is something we can comment on. Okay, so if you were to track this downwards, what you would see is still this, right? Because the chlorine is going to leave, right? Along with the hydrogen, one of the hydrogens on the amino group, it gets kicked out. Okay, and that's the thing we want to mention briefly. Okay, so obviously, as a polymer like this forms, instead of water as a byproduct, like we've been getting in all the other examples, you're going to get hydrogen chloride as a byproduct. And there's not much I want to say about that. It's just worth commenting on because hydrogen chloride is a corrosive gas, right? So there might be some kind of scenario where you're asked about the relative safety of making polyamides from, for example, dicarboxylic acids versus diacid chlorides. And anytime you react to an acid chloride with something, you're generally going to get HCl as a byproduct, right? Unless there's some other base around to mop it up. And that usually is a bad thing. All right, so I didn't really go through diacid chlorides very much, but pretty much every single example where we've had a dicarboxylic acid, if you take the OH away and put a Cl there, you get the same kind of idea as what we've just looked at. All right, we're done.